Year 13, Chapter 5, Differentiation, Lesson 2, the chain rule for differentiation. So we're going to start off by recapping what we mean by a composite function. So I will provide an example of such a function. Y equals x plus 5 in brackets all raised to the power of 7. So why is this a composite function? Well, you can see that we start with x, we add 5 to create the function x plus 5, and then we raise to the power of 7. So we get x plus 5 to the power of 7. So this is a function that is composed of two separate parts, the adding of 5 and then raising to the power 7. Now, what I want to consider is how could we differentiate this function with respect to x? Now, you could, in theory, expand this function using the binomial expansion or using Pascal's triangle and then differentiate the 8 terms that you get. But that's quite a long process, and there has to be a simpler way of doing this. And this is where we're going to introduce the concept of the chain rule. And the chain rule is very useful when we're differentiating these sorts of complex composite functions which cannot be differentiated easily term by term in the manner that we're used to using. So let's have a look at the process. So I'm going to start off by saying that we will call a new variable u x plus 5. Now, where have I chosen x plus 5 from? Well, it's the inner function, the first function here. X plus 5 is being raised to the power of 7. So I'm going to say that u equals x plus 5. It doesn't have to be u. I could have used t or another letter. We just quite often see u used. Now, I can then write y in terms of u. So instead of y equals x plus 5 to the power 7, I can say that y equals u to the power of 7. And I'm now going to perform two differentiations. I'm going to differentiate u with respect to x. So du by dx is equal to 1. And I'm then going to differentiate y with respect to u. So this gives me 7u to the power of 6. Perfectly okay. Y is set up in terms of u here, and I'm differentiating y with respect to u. So the differentiation is perfectly valid here. Now, the chain rule then tells us that dy by dx, which is what we're actually trying to find, remember we're trying to differentiate the original function y with respect to x, is equal to dy by du multiplied by du by dx. Now, a lot of people like to think of this as being a situation where the du parts cancel here and here. That's not strictly what happens, but it is a way in which some people like to think of this. So what do we know? Well, we know that dy by du is 7u to the power of 6, and we know that du by dx is just 1. So the answer is 7u to the power of 6. But remember, u is the same as x plus 5. So really, we need to rewrite this as 7, and instead of u, x plus 5 all to the power of 6. So we've completed the differentiation, and you may find the answer interesting to note. So y equals x plus 5 to the power of 7, dy by dx is equal to 7 bracket x plus 5 to the power of 6. Now, you may have already spotted the connection between the original question and the original function and its derivative, but we will come to this a little bit later on. So we're going to have a look at a few examples together in which we will use the chain rule in each of these. So let's work through these together. Question number 1. We're going to start with the function y equals 3x minus 5 all raised to the power of 6. You're going to see a lot of power functions for the moment. Now, the first thing we need to do is identify the innermost function here, which was what we define as u. So u is equal to 3x minus 5. Y can then be expressed as u raised to the power of 6. We then need to differentiate each part separately. So we find du by dx, which is simply 3. And we find dy by du, careful with your letters, don't let them get mixed up, which is 6u to the power of 5. We can then use our knowledge of the chain rule, which tells us that dy by dx is equal to dy by du multiplied by du by dx. And we can fill in the information that we know. What do we know about dy by du? It's 6u to the power of 5. And what do we know about du by dx? It's 3. So the answer is 18u to the power of 5. Or 18, and instead of u, remember, we have this up here, 3x minus 5 to the power of 5. Now again, you will want to compare the question, which is y equals 3x minus 5 to the power of 6, or the original function, really, and its derivative, dy by dx, 18 multiplied by 3x minus 5 to the power of 5. There's a connection here, isn't there? There's something here to do with that idea of multiplying by the power, reducing the power by 1 as well. But there's a bit more to this. Perhaps we can find out the answer if we do a few more examples. So here's my second example. Y equals 5 minus 2x all raised to the power of 8. Identify the inner function first of all. So this is u, which is 5 minus 2x, and then y can be written as u to the power of 8. Differentiate, du by dx is equal to negative 2, and dy by du is equal to 8u to the power of 7. Now, coming back to the chain rule, again, dy by dx is equal to dy by du multiplied by du by dx. And then let's put together the constituent parts of this. dy by du is 8u to the power of 7, and we're then multiplying by du by dx, which is negative 2. What do we then have as the answer? Negative 16u to the power of 7, but we need to remember that u is 5 minus 2x, so we want to express the final answer as negative 16, 5 minus 2x to the power of 7. Now, again, I urge you to look at the question, or the original function, y equals 5 minus 2x to the power of 8, and then look at the derivative of this function, negative 16, 5 minus 2x to the power of 7. Can you see the connection? Can you start to see how we can get from here to here without necessarily having to write out the full level of working that we've had to do here? Let's see if we can spot this using the next example. So, example 3, y equals 2x squared minus 3 all to the power of 4. Notice the inner function this time is not linear. So u equals 2x squared minus 3. Y equals u to the power of 4. We'll apply the same process as previously. Du by dx is equal to 4x, and dy by du is equal to 4u to the power of 3. Now, let's go for the chain rule again. Remember, dy by dx, which is what we're aiming to find, is dy by du multiplied by du by dx. Don't cut corners at this stage. You need to work everything out fully until we spot exactly what is happening here. So this is 4u to the power of 3 multiplied by du by dx, which is 4x. So our final answer here is, well, our intermediate step before we get to our final answer is 16 u to the power of 3 multiplied by x. Now, we want to replace u with what u is in terms of x, so we're going to write this as 16x, and then in place of u, 2x squared minus 3 all to the power of 3. So an interesting one, the original function is this, and its derivative is this. So there's a bit more to this. It's not just about multiplying by the power and reducing the power by 1. There's something else going on as well. Can you spot it? So now it's your turn. There are 3 functions here, all of which are composite. You are going to use the chain rule to differentiate each of these. Now, even if you think you've spotted the pattern that's going on here, for the moment, please work through these using the full chain rule technique. And later on, we will discuss the quick method that can be used to replace some of this working, but it is important for you to practice the full method to start with. So pause the video, try these questions, the answers will come up in a moment. So the answers will come up in a second, check whether you have got these correct. So here are the answers, check you're working carefully to see that you've got to the same 3 final answers. So let's have a look at these results in a little bit more detail. In the first question, the function is y equals x plus 5 all to the power of 7. Now look at that. This is the power, and we do end up multiplying the original function by the power, and we then do reduce the power by 1. So looking at it very simplistically, it seems like that is what has happened in all the questions. However, there's a bit more to it. Look at the next question. The original power is 6, and we end up with a new power of 5. So yes, 6 take away 1 gives us the 5. But out in the front, we have 18, not 6. So where has the extra factor of 3 come from? Well, it's come from the derivative of the inner function here, the 3x minus 5. So if we were looking at finding dy by dx, we multiply by the 6, we reduce the power by 1, which gives us a power 5, but we then multiply by the derivative of this inner function, and if we differentiate 3x minus 5, this gives us 3. And this then simplifies to give us 18 brackets 3x minus 5 to the power of 5. Now, does that work in other examples? Well, let's pick another example at random. Let's pick this example over here. So we start with a power of 4. So dy by dx, I could multiply by the power of 4. I then reduce the power of the overall function by 1, which drops it down to a power of 3. But I must then multiply by the derivative of this inner function. Now, what is the derivative of the inner function? Differentiate 5 minus 3x and we get negative 3. So this then simplifies to give me negative 12 5 minus 3x all cubed, which is the answer that we have here. Let's look at the final example and see if the same thing happens here, so this question here. So dy by dx, well, let's start with the original power, which is 7. So we multiply by 7 and drop the power down to 6. But we must then multiply by the derivative of the inner function. What's the derivative of the inner function? It's 4x. So this then gives me 28x, 2x squared plus 4 to the power of 6, which is the answer that we got here. So I sometimes like to call this method the quick chain rule. And what we're going to now do is have a look at this process in a little bit more detail. So we need an example to work with. And I'm going to choose y equals 5x minus 3 all raised to the power of 8. So I effectively have y equals something, some function raised to the power of 8. Now, if we look at the chain rule in its long format, we start by identifying the inner function, which I call u. So u is 5x minus 3. We then write out what y is in terms of u, so y equals u to the power of 8, and we then differentiate each part separately. So du by dx is equal to 5, and then separately dy by du is equal to 8u to the power of 7. Now, the chain rule then tells us that dy by dx is equal to dy by du multiplied by du by dx. So let's work out the two component parts. Dy by du, we've just written in green, is 8u to the power of 7. And du by dx we have in yellow, it's 5. This then gives us 40u to the power of 7, which we can simplify by replacing u with what we have up here. So the answer is 40, 5x minus 3 to the power of 7. So that's the long form of the chain rule. Let's now have a look at applying the quick chain rule. So remember, I said I had y equals something to the power of 8. So it's a power function, or a polynomial type function. Something is being raised to a power. There's a power involved here. So we know that when we differentiate and there's a power involved, we multiply by the power, we reduce the power by 1. So we have 8 bracket, and then the something is raised to the power of 7. But we know that the inner function is 5x minus 3. And what we now have to do is multiply by the derivative of this inner function. What's the derivative of this inner function? Well, it's 5. Now, we can see straight away this will simplify down to the final answer that we have here, but let's compare the two methods on the left and the right. Can you see that this 5, which we have here, well, we multiplied by a 5 back over here in the long format of the chain rule. And this part that we have here is simply this part over here. But on the right-hand side, we have 5x minus 3 rather than u. So the quick chain rule does everything that the long format of the chain rule does. It's just a little bit quicker. And it's absolutely fine to use either method when you're differentiating, if you're answering an exam question. If you feel confident and comfortable using the quick chain rule, which I hope you'll do following some practice, use the quick chain rule. If you're less sure, write the full working out on the left-hand side. We're going to do one last example. We'll use both methods again. So the long format, first of all, identify the inner function here. U is equal to 4x cubed minus 3. Write out y in terms of u. Y is u to the power of 7. And differentiate. Du by dx is 12x squared, and dy by du is 7u to the power of 6. So remember, the chain rule then tells us that dy by dx is the product of these separate derivatives, dy by du multiplied by du by dx. And we can then fill in what we know. Dy by du is 7u to the power of 6, and du by dx is 12x squared. So this then simplifies to give us 84x squared, and then instead of u to the power of 6, we would write 4x cubed minus 3 all to the power of 6. And that's our final answer. Now, that of course uses the long form of the chain rule. can we get to the same answer using the quick chain rule? I'm confident that we can. So dy by dx, notice it's a power function. That's the crucial thing here. It is something raised to the power of 7. Later on, when we explore differentiating different types of function, it'll become increasingly important to identify what sort of function you are dealing with in each case. So the quick chain rule tells us it's a power function multiplied by the power first of all, so that's 7. We then have the function, the inner function I should say, raised to 6, the power 6, so we've multiplied by the power, we've reduced the power by 1, but we must now multiply by the derivative of this inner function here. So what is the derivative of the inner function? Well, it is 12x squared. And already you can see this is just going to give us the same final answer that we got to using the long form of the chain rule. So the part where we're multiplying by the derivative of the inner function just equates to this part here in the chain rule, which you can see from the long form of the chain rule. Now it's quite nice to see whether we can actually generalise this. So what if we have y equals k multiplied by ax plus b all raised to the power of n. Now it's a power function, and I want to be very clear that a, b and k are constants, so they're just letters which represent numerical values or constant values. So what would dy by dx be equal to? Well, let's look at each part very carefully in turn. Well, the k is just a constant that remains in place like that. Now the n, we need to multiply by the power and then reduce the power of the overall function by 1, the innermost function by 1. So it becomes multiply by n, and then the power becomes n minus 1. And we then need to multiply by the derivative of the inner function. What do we get if we differentiate ax plus b? We simply get a. So that would be the answer, and of course we would simplify this. But we can generalise further because, as we've seen in the previous examples, the innermost function isn't necessarily linear. It could be 2x squared plus 4 instead of ax plus b. And later on, when we look at differentiation of trig functions, log and exponential functions, you will look at even more complex inner functions. So the most general example that I want to look at is what if we have y equals f of x, and this f of x is being raised to a power of n. So dy by dx, let's see if we can work it out. So the first thing we need to make sure we're clear on is that this is a power function. Something is being raised to a power. A function, an inner function, is being raised to a power. So we multiply by the power n. We reduce the power by 1, so there's n minus 1. And then we need to multiply by the derivative of the inner function, which is f dash x, whatever f dash x is equal to. And here we can see the 3 stages written out in words. Multiply by the power, reduce the power by 1, multiply by the derivative of the inner function. And that is how we apply the quick chain rule. We're going to have a look at a series of examples now. Now in each of these questions we're going to differentiate the functions using the quick chain rule. It's up to you as to whether you work through each example with the video or whether you have a go and then check your answer afterwards. So feel free to pause the video, try the question and then fast forward to check your answer, or work through the working. You may want to work through a few questions with the video and then try some of the later questions on your own. They start off simpler and then become more complex. So y equals 6x plus 1 to the power 9, so something raised to a power. dy by dx, I've multiplied by the power, 9. I've reduced the power by 1 to give me 8, and then I'm going to multiply by the derivative of the innermost function, which is a derivative of 6. So the final answer will be 54, 6x plus 1, all raised to the power of 8. Question 2. Y equals 3 bracket x squared minus 2 all to the power of 6 dy by dx. Now this 3 here can just be part of the answer like this. I'm going to multiply by the power of 6, reduce the power by 1 to drop down to 5, and then I want to multiply by the derivative of the inner function, which is a derivative of 2x. Tidy up the answer, and we end up with 36 x squared minus 2 all to the power of 5. Question 3, a slightly more complex inner function here. So as before, multiply by the power, reduce the power by 1, so it drops down to 4, and then multiply by the derivative of the inner function. Now the derivative of the inner function is 4x minus 3. And we might just tidy this up. 5, 4x minus 3, 2x squared minus 3x to the power of 4. Now, question 4 is an interesting one because people don't always recognise that this is a power function. So we want to rewrite this as the inner function f of x raised to the power of a half rather than as a square root. So we want to rewrite this as 4x plus 3 to the power of a half. So multiply by the power first of all, so that's a half. Keep the function as it is, 4x plus 3. Now we need to reduce a half by 1, so it drops down to negative a half, and multiply by the derivative of the inner function, which is 4. What does this then simplify to? 2 brackets 4x plus 3 to the power of negative a half. So question 5, again, people might not necessarily recognise this as a type of power function, but we want to rewrite it as a function raised to the power of negative 1. So 4 brackets 3x minus 7 to the negative 1. dy by dx. Now this 4 that's at the front can just be here at the end. We want to multiply by the power, which is negative 1. We want to reduce the power by 1, which becomes negative 2, and we want to multiply by the derivative of the inner function. Differentiating 3x minus 7 gives us 3. So what do we have as a final answer? Negative 12, 3x minus 7, all to the power of negative 2. Question 6, have a look at it. How would you rewrite this function? Well, I think I would want to rewrite it as 6 bracket 4 minus 3x to the power of negative 5. So we want to rewrite this so we can see the power clearly. So dy by dx, well, this 6 here at the start will just be part of the answer, a multiple. We need to multiply by our power, which is negative 5. Reduce the power by 1, so it becomes negative 6. And then multiply by the derivative of this inner function, which is negative 3. So quite a lot to do in this particular question, and we get to a final answer of 90, 4 minus 3x to the power of negative 6. So question 7, again, recognise that this needs to be rewritten. And we want to rewrite this as f of x raised to the power of negative a half. Now, the 8 at the beginning is just simply there as part of the question. It's just a multiple, but it's the 2x plus 1, which is being square rooted in the denominator, that I want to rewrite as 2x plus 1 to the negative a half. So dy by dx, the 8 is simply just part of the final answer. Let's multiply by the power of negative a half. let's reduce the power by 1, so that becomes negative 3 over 2, negative 1.5. Some people like to write that, but it's much better to use top-heavy fractions rather than mixed numbers. Multiply by the derivative of the innermost function, which is 2, and then simply simplify your answer. So it becomes negative 8, 2x plus 1 to the power of negative 3 over 2, and we are finished. So we're going to look at one final example where we apply everything we have done to a slightly more complex problem. So consider the function y equals x squared minus x minus 2, all raised to the power of 4. We're going to find and classify any turning points of this function. Now we know at any turning points, i.e. maxima or minima, the function must be stationary, so dy by dx must equal 0. So this means that we need to find dy by dx. Now, can you see it's a composite function and it's a power function? Something is being raised to the power of 4, the something being x squared minus x minus 2 to the power of 4. So let's multiply by the power of 4. Let's reduce the power by 1 to give us 3, using the quick chain rule here. And let's multiply by the derivative of the innermost function here, which is, of course, 2x minus 1. So our derivative is 4, brackets 2x minus 1, brackets x squared minus x minus 2, all to the power of 3. Now, remember, we are trying to find stationary points. So we need to set 4, 2x minus 1, x squared minus x minus 2 all to the power of 3 equal to 0. Now, if we solve this, then the options we have are that 2x minus 1 equals 0, which would give us x equals a half. And the other alternative is that x squared minus x minus 2 equals 0, so that the cube of this result becomes 0. Now, this then leads us to a mini quadratic equation, which we can factorise. And this then leads us to the possibilities of x equals 2 and x equals negative 1. And we now know that we have 3 possible stationary points, and we have to identify what's going on at each of them. So let's substitute these x values into the equation for the curve to find out the y values. Now, interestingly, when x is equal to a half, we get y is equal to this slightly unpleasant looking fraction here. And then at x equals 2 and x equals negative 1, y simply equals 0. Now, we have the option of trying to differentiate again, but if you note the derivative that we got, this would involve quite a complex differentiation. We would in fact have to use the product rule, which we haven't yet learnt about. So what we're going to do is evaluate the value of dy by dx at either side of each of these x values. So as you will know, I like to set this up in neat tables. We know that dy by dx equals 0 at each of these 3 points. What we don't know is the value of the gradient at either side of these 3 points. And what we can do is substitute into this result here. Now, this is where I advocate using your graphical calculator and storing values as x. So you could set 0.25 as x and then type out the derivative in terms of x to allow it to be evaluated. This is much easier than typing in negative 1.5 all squared minus 1.5, and you're much less likely to make a mistake if you do it this way. So starting with 0.5 and substituting in, we can see very clearly that we get a positive gradient, a 0 gradient, and then a negative gradient. So this point here is a maximum point, example A. Now with the stationary point B, we find that we get a negative gradient, a 0 gradient, and a positive gradient. So this is clearly a minimum point here. So I've identified A and B, And now let's look at example C and see if we can identify what this is. So for the final part, we can see for C that we get a negative gradient, a zero gradient, and a positive gradient. So this is clearly another minimum point.